Okay, let's go ahead and get started for the day. Last time we looked at like some networking stuff in an information transfer in a more general sense. Today we're going to dig into TCP/IP, which is the protocols that largely underpin the entirety of the internet, and we're going to take a look at how those work. So previously looked at that OSI model. We talked about how it has that layered approach to communication protocols. It's kind of a standard for making a networking system, and that you should have things divided or stratified into these layers. And what that does is it allows protocols that can work across a variety of physical network systems and for a variety of different applications, where different layers of that handle a different part of the communication. And the ability to interconnect systems like that is really necessary for something like the internet to exist. That for the internet to exist, you have to have a whole bunch of networks all across a large geographical area, all interconnected and able to talk to each other. And the OSI model helps with that because it allows you to have different kinds of physical network that then connect together and have streamed data and datagram data and logical data work, and a variety of applications that they can then use those subsystems to do application level things. And so it's really important to have that layered approach. So we're going to see that even though there's some blurring of lines between the layers as they're defined in the OSI model, TCP/IP still uses that same kind of layered approach. And TCP/IP is the kind of foundational protocol suite of the internet. And notice I say protocol suite. It's not just one protocol. That's why it has a TCP part and an IP part. It's got multiple layers that are kind of encapsulated together, grouped together as part of TCP/IP, and they work together to make something like the internet exist. Okay, so what is TCP/IP? Well, it's a layered set of protocols for network communication. Each layer provides its own type of functionality. Think of it and there are functions that we can use to talk to it. So think about it like a library of routines that each has a set of purpose or defined purpose to them. It's designed to be used on the internet to connect things in widely spread geographic regions, but it also works on land. So you could actually even use TCP/IP to have two programs communicate with each other on one computer system. It was created in the 1970s by the Advanced Research Project Agency as a way to interconnect a lot of computer systems at these different research institutions. And it was built on what's called a packet-switched or a connectionless paradigm, meaning that unlike the telephone system, when you're on the telephone system and you pick up the phone and you make a call, the way the telephone system worked is it was a connection-oriented paradigm where you had a connection from your phone through to the phone on the other end. And so when you were talking, you had a wire that connected from you to the central office, from the central office to some switching station, that switching station, another switching station, that one to another central office, and then from there to the other phone. You can think of it like a wire that went all across the country from your phone to the other phone on the other end. It's a connection-based paradigm. But TCP/IP was built on this connectionless paradigm where you take a packet, you toss it into the internet, and it finds its way to its destination. And one of those blocks of data is called the datagram. And so if you have a larger amount of data than will fit in one datagram, then you have to send multiple datagrams and sequence them in some way. You have to have some way of sequencing them. And you can think of a datagram as a packet. It's a collection of data. It's sent together as one single unit or one single message. And each datagram gets sent through the network individually. So, in other words, if you have a large amount of data to send or a stream of data to send, it's divided up into these packets called datagrams. Each one is sent through the network individually. So that's essentially what we're talking about with TCP/IP. Everything is these datagrams. Even if you have a streamed connection, under the hood, it's datagrams. If you have a datagram, then like UDP being sent, a UDP packet being sent, then it's still sent through individually the same way that the stream is, but the stream divides it up for us, puts it back together for us. Okay, so the layers of TCP/IP are a little bit different, a little more coarse-grained than what we saw with the OSI model. But the application layer, that would be the high-level protocol that's using the TCP/IP service. And you might have a protocol at that level. Could be FTP, could be HTTP, could be one of the mail protocols, or it could be some proprietary thing we make for our own game server that we're creating. It could be something very simple, could be something very complicated. But that application layer is usually just using the services of TCP and IP to do its job. And it defines its own protocol for how things get encoded, how they get decoded, and what the actions are. But below that, we have the transport layer, which is the TCP layer. And that's where the TCP part of TCP/IP lives. And that provides services for reliable session-oriented communication, meaning you open a connection, you send the data. If it says it's sent, you're guaranteed that it was sent, guaranteed that it was received on the other end. And when you're done, you close the connection. So notice that means TCP/IP provides a service that makes it seem like a connection-oriented protocol when it's really all under the hood packets. Now, the TCP layer is responsible for sequencing, meaning dividing the data up, putting sequence numbers on it, making sure that any missed sequence numbers get resent, making sure any duplicates are tossed out. That's what TCP does. Now, below that is the IP layer, and what the IP layer does is it provides the basic service of getting a datagram onto the network, and ultimately the addressing scheme is what's used to route the packets to their end destination. And then below that, below TCP/IP, we have the network interface layer, and that's the actual protocol that manages a specific network type like Ethernet or Wi-Fi or something like that. So that's the part that's actually creating the actual physical packets. I guess they're not really physical, but the actual packets that are going onto the physical network. So applications use TCP, which sits on top of IP, which sits on top of and uses the network interface below that. So notice we have kind of more of a 4-layer approach here rather than the 7 layers that we saw with that. So in other words, network interface layer here, that combines the physical layer and the data link layer. IP is above that, the internet layer, and then above that is the transport layer and the session layer kind of wrapped together inside of one. And then up here, we have the presentation layer and application layer kind of rolled into one. But all of the same functionality is there. It's just some of it's a little more coarsely assigned in a typical TCP model. Okay, so the TCP/IP application layer, that's really outside of the scope of TCP/IP. That's up to the person writing the application. But you are going to, when we write code that does this next class, you're going to write code where you're going to write an application and it's going to make calls to the TCP/IP subsystem to configure that network subsystem and exchange data with the TCP/IP network subsystem through function calls. In other words, think of TCP/IP as a library. So you're going to make calls to that to configure it, to set it up, and then to interact with it to send data, receive data, open connections, close connections, and so forth. So that TCP/IP is below the application layer. But the application layer, what it contains is the features of, in the OSI model, would be application and presentation layers. So in other words, if we want encrypted data, we'll do that at the application layer. If we want an application-specific protocol, we will implement that ourselves outside of the layers of TCP IP. So an application would be anything you can think of: network game, web browser, file transfer application. It could be something, an industrial networking system that monitors machines. It could be an Internet of Things security system. It could be anything that uses the internet. But it's going to sit on top of and make use of the TCP and IP function calls. Now the TCP layer, TCP stands for Transmission Control Protocol. And it's, like I said earlier, TCP is the part that's responsible for making sure the data gets through to the other end. And it also is, how does it do that? It keeps track of sequencing, what datagrams have been sent, which ones fail, if they do fail. it automatically will cause them to be retransmitted. If any of them are damaged, same thing, retransmitted. If a message is too large for one datagram, TCP will split it up into several, make sure that they all arrive correctly and in the correct order with no duplicates and none missing. And the way that it keeps track of those is it adds a header onto the data, because if you're going to keep track of a sequence, you need to have a sequence number. If you're going to keep track of which ones have arrived and which ones have failed, you need to have some mechanism for keeping track of that. And it adds a little bit of data, this TCP header, to keep track of that. Now, below that, the IP layer, that doesn't care anything about sequencing or anything about missing packets or reliability. All it does is takes the TCP datagrams, adds addressing and routing information onto them. Think of that like an envelope. So inside the envelope, you have pages that have page numbers. The envelope itself doesn't have page numbers. It just has for sequencing, it just has the address, who's it going to, where's it coming from, and postage on it or whatever. In this case, there's no postage. It's just who's it going to, where's it coming from, what kind of information is in it, and so forth. So IP's job is to find a route to get the packet through the internet to the destination using the addressing information. And IP addresses, is important to understand, those are logical addresses that are configured for your machine. If you can have an ISP that you connect through, a lot of times the addresses are assigned dynamically. So you get a dynamically assigned IP address. There's a system called DHCP that does that, Dynamic Host Control Protocol, or Host Configuration Protocol, depending on who you ask. But DHCP essentially is one way to assign things. You can also have machines that are assigned static IP addresses, where you configure it and say, this is going to be your address. Usually that would, you have an internet service provider, and you would get a static IP address assigned to you from them. You assign it to a server, and now your server has some address that it lives at on the internet. Kind of like the phone company assigning a telephone number. An IP header is added to keep track of that, just like on the outside of an envelope. You've got addressing information. The same thing is true here. The IP header is added to the data that's inside of that, and it has that address, the logical addressing information added to it. Now, the network interface layer, we're going to specifically focus today on Ethernet. There are many other network systems, but Ethernet and Ethernet variants are a popular choice. You see them everywhere. Wi-Fi itself was built on kind of the Ethernet model, but over wireless. And Ethernet itself has multiple variants, 10 base 2, 10 base T, 100 base T, 1000 TX, so gigabit, 100 megabit, the original 10 base T, 10 megabit, original 10 base 2, which was a little coax cable. There are a number of varieties for Ethernet, but it's a popular choice, so that's one we're going to focus on today. But note that you could have the TCP and IP packets wrapped in a different kind of network interface layer packet structure. Fiber optic, some sort of alternate communication form, carrier pigeons, whatever. But so the physical layer, notice that TCP and IP are not a specific kind of hardware. They are a logical addressing system that's built on top of, or is compatible with a variety of lower level network systems. All right, so Ethernet, it was designed originally as a broadcast medium. Each card has its own unique address assigned to it called the MAC address, and that's a physical address that's assigned to your device. Same thing is true for Wi-Fi systems. So if you have a device that has Wi-Fi capability, like a smartphone, it has a hardware address assigned to it. If you have a PC with a network card or a network card built in to the chipset of the motherboard, it has a MAC address that was assigned to it at the factory. Now, what the Ethernet layer does is it basically converts the IP datagram into an actual packet that goes across the network. Now I want to make a distinction here between two things. Notice I've been kind of interchangeably using packet and datagram, and I'll probably continue doing that. It's really just a block of data. But notice a datagram is kind of like a logical grouping, where a packet is something physical that's going to go across the network or go across the wires. And sometimes you might have an IP datagram that's too big to fit into the packet size for a network. And you see that sometimes in wireless systems, also in wired systems, where the physical packet size, the MOTU, they call it, we'll see that again later, is or MTU, the maximum transfer unit size, is such that the packet or the datagram was bigger than that. And then you have to divide that up into smaller packets and then put them back together again. And Ethernet has a way to do that. We'll talk about that later. But the Ethernet header is added to keep track of the layer information, so it has its own header. And that layer's information includes the hardware address of the machine that it's going directly to, and some other stuff about the version and so forth. We'll look at that more carefully here in a second. Now, there are a variety of variants of Ethernet, 10 base or 100 base T, Wi-Fi, 10 base T, gigabit Ethernet, which is the 1000TX, 10 base 2, which I mentioned, and so forth. And even within Wi-Fi, there are a number of standards for that. So 802.11a, 802.11b, 802.11g, 802.11n, and so forth. There's a variety of those there. But ultimately, it boils down to, here's a block of data that's going across the physical network from my machine or this machine to the next one in the chain. All right, so speaking of datagrams versus packets, the technical difference between those, again, just so you have a visual for that here with a slide. The datagram is the right word to use when describing TCP/IP data blocks. In other words, if you're at the TCP or IP level, it's a datagram. So a datagram is a unit of data that TCP/IP deals with. A packet is a physical grouping of data that appears on an actual network. So that would be so you have an Ethernet packet, you have a TCP or IP datagram. So an IP datagram, Ethernet packet. Now really, they're still just a block of data, and a lot of times they're one and the same. That an Ethernet packet has a TCP datagram wrapped inside of it. And we'll see that here with a little more detail in a second. Now, in most cases, it's true that datagrams and packets are one and the same. A packet simply contains a single datagram. So there's very little difference in most cases. However, if you're like I said earlier, if you're sending a datagram on top of a system that has smaller maximum packet sizes, like X.25, which was an interface for sending data, that has to break the datagrams up into 128-byte packets. And you also see that with certain proprietary wireless systems where they have the maximum wireless packet size is 128 bytes or 64 bytes or even 32 bytes. Well, how do you send a datagram that's hundreds of bytes or 1,000 bytes across something that can only handle things that are 128 or 64 or 32? Well, you have to divide it up. But that's invisible to the IP layer because the packets are going to be divided up, sent across as multiple packets, put back together into a datagram before being processed by TCP/IP. So we don't, at the TCP and IP level, we don't have to worry about that. It's up to the data link layer and the physical layer to handle that in the drivers of that system. So with most media, there are advantages to sending one datagram per packet. So with Ethernet, it tends to vanish for the most part. We'll talk more about that later on. Okay, let's dig into some details now. We talked about TCP having a header. And remember, this is inside the innermost thing that's being added other than your application protocol header, if you have one. So at the TCP level, you notice there's a couple things here, that it's 20 bytes long, 28-bit bytes long, And notice I've divided this up. Each of the spaces between these two plus signs is 1 bit. So that's 1, 2, 3. So this is 16 bits going across. There's another 16 bits. So that's a 32-bit word going across here. So that's 4 bytes going across. So if we do 4 times 1, 2, 3, 4, 5, the header is 20 bytes long. So relatively small. It's a small header. And we're going to dig in and look at some of the parts of this header here going forward. But the first part you might notice is at the very beginning, we have the sequence number, or the source port, and a destination port. So every TCP datagram has a port number that it's associated with. And a port number, a way to think of that is in the early days of computing, they had a need for a computer to handle multiple applications sharing that network. In other words, you might have to have multiple things serving data and listening for connections. You might have multiple things using outgoing, making outgoing calls and sharing that. So it's not too dissimilar to a phone or a phone system in an office where there are multiple extensions. And so as a call comes in, it can get routed to the correct extension, and then that person is using the phone line on their extension. When they make an outgoing call, they pick up their extension and they dial it, and they're using their extension to talk out on one of the phone lines. And so, for example, my office has multiple incoming phone lines, but we have, I don't know, 20 or so phone extensions that we use. So all those phone extensions in here have their own extension number. That's what a port number is equivalent to. So the idea of a port number is a way for the TCP system to peacefully coexist with other programs that are using the same TCP system. And notice there are the port numbers are 16 bits, so each computer system could have up to 536 port numbers that are available. Although some port numbers are reserved for certain applications that are probably already using them. So you just can't pick any one that you want for your program because it might already be in use. And if you are going to pick one and use it, make sure that it's one that's available. And if you're going to implement a standard service like your own web server, then you probably want to use one of the standard ones and make sure nobody else is using it. No other program is using it on your host. All right, so notice when you make send one of these datagrams, it tells what port number it's going to, and it tells what port number it came from. And the reason you have to say what port number it came from is when they talk back to you, they're going to use that destination port. Also notice we have this 32-bit sequence number, a 32-bit acknowledgement number. The sequence number, it tells what packet number we're on. We'll talk more about that in a second. And then the acknowledgement number is used going the other way to say, hey, I got all the packets up to this one. Then there's this offset. There's the set of flags here, which we're going to talk about. Urgent flag, acknowledge flag. We'll talk about the rest of these here in a second. There's this thing called a window size, which we'll talk about. And then notice that there's a checksum here. That's the checksum of the TCP data that's up here. And then we have this thing called the urgent pointer, which we'll talk about in a second. And then we have our data. So in other words, this header, this 20-byte header, is just added on to the data that's being sent. And this data that's being sent is variable length. It could be 1 byte. It could be more bytes. But all of that has this header attached on the front of it. All right, so let's look at those in detail. We talked about the ports already. Those are numbers that allow the TCP subsystem to keep track of different conversations, what I'm calling conversations and streams. In other words, it allows multiple applications to share that network and use it simultaneously for different tasks, like phone extensions. Notice that each end has its own extension listed, its own port listed, local port, remote port. So the source port is called the local one. The destination port is called the remote port. Again, think of phone extensions. If you call from, for example, my company on one of the phone lines, it uses an extension. And if I call somebody at another company and they have an extension, my extension number is talking through that phone number to their phone number and eventually connecting to their extension. So this is the local, that's my extension, and this is the one that it's going to go to on the far end when it gets there. Okay, the sequence numbers are used when we have a large stream that needs to be separated into multiple datagrams, and they're used to reassemble the data correctly on the other end and verify that no parts are lost. The sequence number doesn't count the datagrams specifically. In other words, it doesn't go 1, 2, 3, 4, 5. It doesn't count like that. It counts based on the octets of data that have been sent. So if there are 500 bytes of data in each datagram, the first datagram would be number 0, the next one 500, the next one 1,000, the next one 1,500, 2,000, 2,500, and so forth. So think of those kind of like page numbers in a book or issue numbers of a magazine, that it's going to increase, but it's going to increase in blocks of data that are by the byte, not by the individual packet number. And the reason they did that was for efficiency of if you have a packet that gets missed, you still want to stick the one, let's say you had, let's think of it as a count. Or let's just think about these ones here. So 0 came in, 500 came in, but 1,000 was lost, and we got 1,500. Well, we want to go ahead and put that 1,500 into memory, but if we didn't have the offset number here, we wouldn't know where to put it into memory. So this allows me to put it in the correct offset location and then fill this one in later when it comes in, rather than just having to hold on to this and wait for that one to come in. So it's for efficiency that they did that. Also notice there's that acknowledgement number that's used to verify delivery of previous datagrams, and in that case the acknowledgement number is used on an acknowledgement packet that gets sent back, and so when a packet comes in that has acknowledgement number field filled in, that's acknowledging a packet that you've received all the data up to that number. So for example, if we send an acknowledgement packet back with 1,500 filled in as the acknowledgement number, the sending in now knows that all of the packets from 0 up to the one labeled 1,500 has been received. And at the TCP level, the driver says if I don't get an acknowledgement within a certain amount of time, I'll resend that one. I'll resend the ones that haven't been acknowledged. Okay, moving down that header, we have that 4-bit data offset. That's the length of the header in 32-bit words. So that 4-bit data offset, for the most part, is usually 20 in 4-bit words. So it usually has a 5 in that position, but it could be as much as 60, and that allows you to have kind of optional header data that's provided that's after the normal header, but before the application data. And that just allows you to have, to use TCP to send additional header information if necessary. But that can range from 20 bytes up to 3 times as much, 60 bytes worth of additional, or worth of data for the header size. So that offset doesn't tend to change. In most cases, that's just going to indicate 20 bytes. So it'll have a value of 5 in there. It'll always be 20 bytes, and that says this is where the application data starts. Think of it like a index forward that says this is how far off the beginning of the header the data starts. There's 6 bits that are reserved that aren't really used for anything, and now we have the set of TCP flags, and these are just single bits. So there's an urgent pointer flag. There's the acknowledgement number is valid flag. There's this push flag, which says the receiver should pass that data to the application as quick as possible. There's this reset flag that resets the connection. There's a synchronized sequence numbers to initiate a connection flag. And then there's a fin flag, which says the sender is now finished. That means that I'm done with sending stuff when I get a packet that has the final flag set. There's that window size. The window is used to control how much data can be in transit at any given time. So it would be, so the way that TCP does not work, it doesn't do a datagram, an acknowledgement, a next one, acknowledgement, next one, acknowledgement. They realized that, especially since the internet was designed to be implemented across a large geographical area, that would be too slow. So what they do is you send like packet, or maybe I should say datagram. You just start sending out these datagrams. But the problem there is you don't want to send them out too fast, or you might overrun the capacity of a slow system or overburdened system on the other end. So what happens here is each end indicates how much new data is currently prepared to process by putting a number of octets in that window field. And in other words, as acknowledgements come in, if the window size that you're sending with the acknowledgement gets reduced, then what happens is the sender can then slow down the transmission, or if it goes to 0, then the rule is the sender has to stop sending stuff for the time being. So in other words, it's used for kind of this handshaking where you can say this is how much it's okay to have in transition at any given time. If that goes to 0, they're saying, hold on, I can't handle any more data right now. So it's almost like a capacity that gets exhausted and then refilled as it processes things. So if it goes to 0, it means it has no more capacity right now. And it's a form of what we would call adaptive flow control. So rather than just saying hold on or go ahead, it's saying an amount. So hold on means what happens when it gets to 0, but it's saying go ahead and I'm really good. I have a lot of window size, a lot of capacity, and it'll start shrinking as they get under load and or get a backlog of stuff. And if that goes to 0, the sender needs to stop sending. The cool thing is TCP handles all that for us. We don't have to think about any of that. It just does it behind the scenes for us. So, all right, final couple things here. The TCP checksum. That's a 16-bit number that's computed by adding up all of the bytes in the datagram. It's a little more complicated than that, but that's the gist of it. It's kind of an additive arithmetic checksum. The result of that computation is put in the header. What happens when the data is received at the other end? The other end computes the checksum again. If they match, then the data was received correctly. If they don't match, then something bad happened and to that data. It got corrupted in some way. And that data is thrown away and not acknowledged. So in other words, if we get a bad packet, we say, I calculated the checksum, I checked this, it's wrong, throw it away. Do not acknowledge it. And then finally, the urgent pointer. The urgent pointer field allows one end to tell the other end to skip ahead in its processing to a particular byte number, a particular offset. And that can be useful for handling asynchronous events. For example, you type a control character that interrupts the output. You could say, hey, jump ahead to this. Even though I've already put this other data in, here's something important I want you to jump ahead to. And that urgent pointer is used to jump ahead to that position that's specified, but only if that urgent flag is set in the packet. All right, so here's the summary of that again. You'll notice in this TCP datagram, there is no address. There's no address for who it's going to or who it's coming from. And the reason is because this is, again, a layered approach. That TCP's responsibility, remember, was guaranteeing reliable delivery and sequencing and transferring the data as datagrams as part of a stream. And you'll notice that's what all this deals with. The port number to get it to the right application, the sequence number to make sure they all get put together correctly on the other end, the acknowledgement number to ensure reliability, that all of them were received. The flags are related to that reliability as well. The window size to handle flow control of the stream, and the checksum to verify the integrity of it. And the urgent pointer to jump ahead if necessary. All right, now let's do the same thing. Let's dig in and look at IP. So IP, just like TCP, is also 20 bytes, but the layout of the packet is different because it has a different purpose. So notice in, first thing to notice in IP, there's nothing about sequence numbers in here. There's this fragment thing we'll talk about, but we'll talk about that in a second. One thing that's important to note, this is an IPv4 datagram header. The ones for IP6, IPv6 are a little bit different, but they have similar things. So we're going to focus on IPv4, kind of the classic 4-byte internet addresses that you're probably used to seeing. But you'll notice the first, and again, this is bits. So this is 20 bytes again. We have the version of IP that's used, the IHL, we'll talk about these in a second, the type of service, the total length, identification, flags, a fragment offset, time to live, which we'll talk about, protocol, the IP header checksum, and then we have addresses. The source address, who it's coming from, the destination address, who it's going to, and then inside of that would be the TCP header, and then following that would be the data. So let's dig into some of these. Version. That's a 4-bit version field. It's used to specify what version of IP was used for that datagram. For IPv4, it's the number 4. For IPv6, it's the number 6. And notice that they can go all the way up to, since that's a 4-bit number, they could go all the way up to 15. So they built in for having IP have different newer versions and being extensible. So for our case, that's going to be a 4 for an IPv4. For 6, it's going to be 6. And notice they put that right at the beginning. The reason they put that at the beginning is it allows you to read those first 4 bits and then know how you want to process the rest of the packet. What's the rest of it? What's the layout of the rest of it look like? So that's why they put that first in there. We have a little visitor here who jumped up on my lap for no reason. I guess there's a reason, but all right. Now the IHL, that's the internet header length, specified in 32-bit words. The IPv4 header has a variable size, the same way that the TCP header did with that offset field. They call it IHL in the IP header for some reason, but it's usually 5, which indicates 20 bytes, but it's a 4-bit field, so the maximum is 15. So again, you could have up to 60 bytes. So similar in nature to the TCP packet that says this is how big the header is. And you can specify that and make it longer if you wanted to add extra stuff in there. Almost always, though, it's 5. But the range of values would go from 5, is in the typical case, up to 60 bytes. All right, the type of service, that's had different uses over the years. A lot of historical types of service uses have been for giving priority, or I guess we'd call it some sort of a increased level of performance to certain kinds of traffic. It's now been redefined to be differentiated services code point, and the idea there is that, for example, voice data packets for a VoIP call are more important to handle in a real-time fashion and prioritize them over something where somebody's browsing the web. So that field now provides a way for routers and other network equipment to prioritize certain types of traffic over other types of traffic. So it's used for quality of service adjustments in certain routers. Oops. All right, that identification, it's next. That's a 16-bit identification field that's going to be used to uniquely identify a group of fragments of a single IP datagram. So in other words, if you have a datagram that is so big it needs to be divided up into multiple IP packets, there's a way to put those. Those cats were flying everywhere. Thanks, cat. But the idea there is you have, for example, one identification number here, the 16-bit number, let's say it's 100. And then over here with the fragment offsets, you can basically say what fragment of that identifier 100 is this. And we'll talk about that here a little more. All right, the flags. There's a 3-bit field they're used to control or identify those fragments. And bit 0 is bit 0 is reserved, has to be a 0. Bit 1 is a don't fragment, meaning that don't allow this to get fragmented into smaller datagrams. And bit 2 is more fragments. And notice that the way those work is if the DF flag is set and fragmentation is required to route the packet, the packet is dropped. In other words, it says never allow this packet to get fragmented. If the subsystem says, well, it's too big for me to send, I need to fragment it, then it just gets dropped. That packet gets thrown away. Now, the more fragments bit is cleared for unfragmented packets, and if it is, and set for fragmented packets. And all of the fragmented packets except the last one will have the MF bit set. So in other words, the more fragments thing. So in other words, if you get a packet with a more fragments set, it knows not to process it yet. There's another fragment coming. When it gets that one, if the MF field is set, it knows there's another one coming. If it gets that one, and the more fragments field is cleared, then it says this is the last one. So it's the way of telling when we are at the last fragment of a group of them. And then the fragment offset is this 13-bit number. That's a field that's measured in units of 8-byte blocks. It specifies the offset of a particular fragment relative to the beginning of the original unfragmented IP datagram. And again, that's used if you have an IP datagram that's too big to go across the physical network. It gets divided up into these smaller packets and then fragmented by putting those offsets in here for a particular identification number. All right, moving down to the next line. There's the time to live field. That's an 8-bit number, and that's used to prevent datagrams from endlessly traveling the internet. And this is one of the things that was very clever that they did, is they said, well, if we're just going to be dropping packets into a network and they're going to get like routed wherever, it could be possible that some of them get routed back to where they started, and they'll say, for example, I send a packet from a machine at the university, it goes up to Columbus. From Columbus, it goes to some router in, I don't know, St. Louis. And that router in St. Louis gets that packet and it sends it out to a whole range of places, one of which is back to Columbus. Well, you don't want the machine in Columbus to get it, send it back to St. Louis, back to Columbus, back to St. Louis, and have packets just in there forever wandering the maze. So the way that they did that, implemented that, is every time the datagram arrives at a router, the router decrements the time to live field by 1. So in other words, it starts out at 20, it gets reduced to 19, and then it gets routed again, and it goes to 18, it gets routed again, it goes to 17. So it's almost like an expiration date for the datagram. If that field ever hits 0, the router discards the packet and then typically sends a ICMP message back, which is beyond what we're going to talk about today. ICMP is the kind of a lower level protocol that deals with things, but it sends back this time exceeded message back to the sender, and then the sender knows, hey, that packet that was dropped in the network eventually died out and was gone. Now, there are some other kind of non-standard uses for this. So if you've ever done a trace route, which shows you the route that your packets take to get to some destination, how do they know that? How do they track that? Well, the interesting thing, that the way that they do that is they'll set the TTL field initially to 1. And then you send out a packet. It gets to the first router, the router decrements, and says, hey, it died. And it sends that ICMP time exceeded message back to the sender. And your program gets that, and then it sets the time to live to 2 and does the same thing. So the ICMP packet, when it comes back, has information about the router that killed that packet. So the idea there is if you start with 1, you know who the first route node would be. If you set it to 2, you know who the second route nodes would be. If you set it to 3, the third one, and so forth. So you just increment that, and eventually you'll have the entire route that your packets are using to get to the from source to destination. All right, protocol. Protocol is an 8-bit field, another 8-bit field. It's used in the data portion of the IP datagram, or it defines what protocols used in the data portion. And those are defined by the IANA, and it maintains a list of protocol numbers. So some of them that are interest to us, ICMP is that Internet Control Message Protocol that we talked about. That's these packets like this that say time exceeded. And then there's TCP packets, which are kind of those sequenced packets that we were talking about. And then there's UDP, which is a user datagram protocol. But there are other ones that are defined as well. But these are the ones that are of interest to us right now. And then the next thing we have is this IP header checksum. And the header checksum is a 16-bit value when a packet arrives at the router. The router is going to calculate that checksum and compare it to the checksum field that's received, just like we did with TCP. If they don't match, the packet's just thrown away. And notice that as routers route your packet, they're constantly changing that IP header checksum. And it's important to note here that the IP checksum, header checksum, is just for the header portion of the IP packet. It doesn't include the data or the TCP stuff or anything down inside of there. And then finally we have the addresses, the source address, the destination address, and those are 4-byte numbers. And for both the sender and receiver. So notice when you talk to somebody and connect to a web page, they have your address. The address field gets filled in for who it's coming from and who it's going to. Just like if I were to write a letter to somebody and write my return address on there, when they get the letter, they know who the letter came from. So that if you may have seen in the news where somebody was issuing threats to somebody, or somebody emailed or some sort of a anonymous email, note that it's not so anonymous if the person doesn't know what they're doing or they're not careful, because it includes the address that goes back to that machine that actually sent it. You can fake these, but by default, when you're sending traffic and connecting to places, they're getting your IP address sent through to them. And note that in IPv4, those are 4-byte addresses. And you may be used to seeing those written in this numbers and dots format, like 146.85.1.1. So this is the first byte, that's the second byte, that's the third byte, that's the fourth byte. And these numbers here will range from 0 to 255, although some of them you're not allowed to put in there. All right, so here's a review. There's the 20 bytes of the IP header. And notice that following that would be the TCP header, following that would be the application data. So right now we have 40 bytes added onto the front of our application data. And let me pause for a second, I'll be right back with you. Okay, so to review the IP header, here's the 20 bytes of that, and then like we said, following that, we've got the 20 bytes of the TCP header and then the application data. So here we are at the Ethernet level. And the Ethernet, if you remember right, that's the actual packets that are going to go across the physical network wires or radio waves or whatever. And if you take a look at that, notice that this is quite a bit simpler than the other ones, that we basically have a destination address, and this is the hardware address, not the logical address that we saw before. So that's a 48-bit address there, 32 plus another 16, and then it has the destination address and then the Ethernet source address, and then it has this type code, and that's it. So in other words, it's just 14 bytes that we're dealing with here. And then also at the end of the data, which has the IP header, and then the TCP header, and then your data, there's this Ethernet checksum, which is this 32-bit or 4-byte checksum that's at the end of that. So you'll notice that this is much simpler. It just has the address of where it's going to, where it's coming from, the type of or type code, the data that includes whatever it is from TCP, whatever it is from IP, or I guess IP first, then TCP, then the data, and then the checksum for all of that. And I want to fix something on here. I don't like this. I feel like that should be over there. All right. Okay, so the source address is the 48-bit MAC address of the sender, so that's the actual hardware address, and the destination is the 48-bit MAC address, and this weird capitalization going on here, so let me fix that as well. But the MAC addresses are, again, the hardware addresses of these, and note that it's the next destination machine. So when you send out a packet to connect to some remote machine, you're really the first address you're putting in there is going to be get generally the address of the router that then the next machine, the hardware address of the next machine it goes to. And the type code that allows for different protocol families to be used on the same network. Not super important for us right now. And then the checksum. That's the Ethernet controller computes that for the entire packet. When the other end receives the packet, it recomputes again, throws the packet away if the answer disagrees with the original. So the checksum is put on the end. It's a 32-bit checksum, and it's a CRC. We talked about those earlier in class. So it's pretty reliable with a 4-byte 32-bit CRC. It's unlikely that you'll have corrupted packets get through. This is actually a much better checksum than the ones that are used in TCP and IP. All right, so Ethernet packet details. Each Ethernet controller comes with an address built in from the factory. Like we talked about, they're pre-programmed. If you have a laptop, it's pre-programmed. Your smartphone is pre-programmed and so forth. And the reason they did that is that would make sure they would never reuse addresses. So the Ethernet subsystem designers allocated 48 bits for the address. And essentially, that means if you're going to make an Ethernet chipset, you have to register with the kind of address assignment authority, make sure that the number, and usually there's a, they're divided up into a manufacturer ID portion and then the serial number portion of that. Some manufacturers might have multiple IDs associated with them. So each machine is supposed to only pay attention to packets. Remember, it was a broadcast medium originally, but each machine is supposed to only receive or pay attention to packets that have its Ethernet address in that destination field. Now, it is possible to put the some Ethernet devices into what's called promiscuous mode, where you say, hey, read a packet from every address. And so you can kind of sniff or snoop on packets that aren't for you. So it's not terribly secure. It's better when you have something like a switch because it routes the packets only to the lines that need to in a wired connection. But with wireless, you can download freely available programs and sniff the Wi-Fi traffic and see all of the Wi-Fi packets that are kind of flying around. Not just the ones for your machine. One thing to note is there is no real connection between the Ethernet address and the IP addresses. IP addresses are logical addresses that are assigned through software. Ethernet addresses are the physical hardware address of your machine, your Ethernet controller. It's assigned by the company that made that chipset or that laptop or that device. So there's no connection between them other than how your machine is configured. Now, each machine also has a table of what Ethernet addresses correspond to what internet addresses that's maintained usually by the internet subsystem. And that's how it knows when you send a packet to like google.com, how it knows who to route that to first. And that machine, when it gets that packet, it unwraps that and it says, okay, where does this IP address? It goes to this next machine that I know about. And it uses that table to look those up, to send those along. So that layering, if you remember how that was divided up, we had the application at the top that uses TCP and IP. TCP sits on top of IP, and then IP sits on top of Ethernet. So that wraps them all together. So the innermost part of the data in one of these packets, an Ethernet packet, would be the application data. And that gets wrapped in a TCP datagram with a TCP header at the front. And then that gets an IP header added onto that. And then that gets the Ethernet header added onto that. So we end up with something that looks like this diagram here. That at the top we have the application data, or the user data. And then that at the application level might have an application-specific header added to that data. And then that data gets passed down to the TCP layer where it adds a TCP header. And then that gets passed down. It created this TCP datagram, which then has an IP header added onto that. And that gets passed down to here to create an IP datagram. And then that has this Ethernet header added onto the front of that with the checksum added on the end. And that's what goes across the network. Now, as this crosses the network, remember that this lower part here is going to constantly get taken off and reformed based on the next machine that it goes to in the chain. But notice the innermost part here, the IP header and TCP header, those are going to stay the same, but the IP header also gets taken off and reformed because it has to reduce the TTL every time one of these gets transmitted. But generally, the TCP header and everything inside of there, that's going to be static across the entire network. One thing else to notice is that looking at this, if you did snoop like traffic, like use a tool like Wireshark or something like that to read either wireless or wired traffic, notice that the application data is all in there and the TCP data is all in there. And if you don't encrypt the stuff that's inside of here, then it's all out in the open for somebody to sniff and see and look at or reverse engineer how this whole thing works. So just keep that in mind if you need to make something that's secure. It might be important to think through the fact that the user data is going to be wide out in the open and visible unless you encrypt that in some way. All right, a couple questions here that I want to walk through is how does the machine know the MAC address of the destination machine? And the answer to that is the end destination machine, it doesn't, has no idea what the MAC address of that is. In fact, the only MAC address it needs to know is the next one in the chain that the data is going to get sent to. How does it know that? That's part of the networking subsystem in the table that it maintains. And there's we mentioned the kind of ICMP packets at the TCP level. There's a whole process of also ARP, the Address Resolution Protocol. There's a whole process by which that happens. It's beyond the scope of what we're going to talk about today. So what stops a machine from using a MAC address of another machine? Well, they're programmed at the factory to be unique, but there are some cases where you can reflash those or change them to match a MAC address of another machine. So the short answer to that is the only thing that's stopping that is the fact that they're programmed at the factory, and it's not always easy to just change it. What stops a machine from using an IP address of another machine? Well, you can only really have IP addresses that are designed to be on your network domain. But the short answer to that is nothing. If there's something that's misconfigured, you could have two machines that have the same IP address, and they will detect that there's something going on, because if they see traffic from another machine show up on their IP address, they'll say something's wrong, and they'll give you a warning or give some sort of error. Another question, how many different possible IPv4 addresses are there? Well, it's 4 bytes, it's 32 bits. So 2 to the 32 minus some of the patterns, like you can't really have a .0. You also, that 127.0.0.1 is a special one. So there are some of those that are reserved for special things, but it's bounded by 2 to the 32. How many different possible MAC addresses are there? Well, it's a 48-bit number, so 2 to the 48th. So a whole lot more of these than there are of those. How many IPv6 addresses are there? Well, the IPv6 addresses much more than there are IPv4, and we'll talk about that later on. Okay, so that's it for today. We came in at just under an hour, which is what I wanted to do, to give you time to look over that, think about that. What I would like you to do is kind of take a look at that stuff again, look at those headers, think about the fact that it's really just your data with a TCP header, and then that with an IP header, and then that with a Ethernet header. That's what's traveling across the network, and the outside ones get stripped off and reformed, every time they go to the next node. The IP one gets stripped off, the TTL changed and reformed every time it goes to the next router. And when the end unit gets it, the TCP part will be the same, the data part will be the same, and the IP part will be the same, but the TTL will have been reduced by some amount. All right, so next time we're going to dig into writing code that deals with this stuff. So in other words, we're going to dig into programming TCP/IP, and we're going to use a library called the sockets library, which is probably one of the oldest standardized ways of doing TCP/IP programming. And that has been around for quite a while, but it still works the same way. It's helpful to know how that works. We're going to look at that from next class from the original standpoint of the C language function calls that make up the TCP and IP interfaces and how you would write code to do that. But all of that also translates to other languages like Python. So we'll probably look at some code in Python as well. Python makes it a little simpler because you don't have to deal as much or worry as much about data types and things like that. But we're going to focus it on it in the at the C language API level, because that's kind of more the native place where the TCP/IP subsystem lives. So that's what we're going to do next time. That's it for today. Everybody stay safe, and I will see you next time.